What if I told you that the shape of the bedrock buried under thousands of meters of ice was the key to future sea level rise? What you see in this photo is a glacial fjord. It's a fjord that has been carved by a glacier over the past tens of thousands of years and is now exposed because the ice has retreated in this region. And this is the sort of landscape that we expect to see under the rest of the ice sheet, but it's just very difficult to see through the ice and see what this landscape looks like. So today I will tell you how we accidentally found a way to unveil this landscape and how we found the deepest point on land. So how did we get there? I'm a glaciologist. I make computer models in order to make predictions of sea level rise and how the ice sheets are affected by climate change. And I've been doing this for about 13 years. While it is clear that sea level is rising today, we can measure it. We don't know to this day whether the ice sheets are going to catastrophically collapse over the next 100, 200 years. It's just very difficult to do. There is a lot of uncertainty in sea level predictions, and it remains too uncertain for policymakers to make informed decisions about how to cope with rising seas. To understand how the ice sheets respond to climate change, we must understand why they are there in the first place. And it is so cold in Greenland and Antarctica that most of the snow that falls every year on the ice sheet doesn't melt away. And so year after year, this snow slowly becomes solid ice. We may think of the ice sheets and glaciers as big pieces of ice cubes that don't move, but they actually move. They flow. It deforms under its own weight, like a very viscous fluid, like a thick syrup in a way. So what you see in this video is a compilation of photos that were taken a few hours apart, and you see 2 years of that compilation. So you can see that the ice is flowing downhill like a river. So eventually this ice that is formed by the transformation of snow into ice is transported to the coast in the form of fast rivers of ice that we call ice streams. And eventually this ice melts, or there's the formation of icebergs that end up melting in the ocean. So if we want sea level not to change, if we don't want sea level to change, we need the perfect balance between new ice formed by the slow transformation of snow into ice and the loss of ice through icebergs and melting. If these two processes balance one another, then we don't see sea level change. But what we've observed over the past 2-3 decades is that our glaciers are accelerating. They're putting more icebergs into the ocean. And also in the Arctic and Greenland, we have warmer summers, longer summers, a lot more melt on the surface. So overall, the balance now, we have about the same amount of snow as before, or maybe a little less, and a lot more mass loss. So that's why the ice sheets are shrinking. Now there is an important point that I want to make. The rate at which the ice sheets are losing mass depends to a large extent on the shape of the bedrock. And there is 2 reasons for that. One that's fairly simple is one reason for which that explains why our ice sheets have been accelerating like this is that there is warm water in the ocean that used to stay away from the ice. It used to not interact with it. And now, because of climate change, we have warm water intrusion into fjords, under the ice, where we have floating ice, and it's melting it from below. And so you can imagine that if the bed is shallow, if we have big ridges, mountain ranges, that may block this warm water that is at depth that is under 300, 400 meters. It may block this warm water. So the glaciers that have a big bump, a big mountain range in front of them, may be protected. But more importantly, the shape of the bedrock can make a difference between a slow, gradual retreat or a fast, unstoppable retreat. And the reason for that is that the ice sheets they weigh a lot. It's a lot of mass, and so over time it has pushed the land below. And in the interior of the ice sheet, many times the bed is below sea level, and you may have that configuration that we call retrograde bed slope, where the bed gets deeper as we move inland. And that's a configuration that we know is unstable. If a glacier starts to retreat in a region where the bed gets deeper and deeper, there is no stopping it. It's going to continue to do so even if we stop burning fossil fuel. So we need to know where the bed is retrograde. We need to know where we have bumps and ridges that may stop that retreat. Otherwise, if we don't have a good representation of the bed, there is no way we can make accurate predictions of sea level rise. But it's incredibly difficult to see through thick ice. It's just very difficult to know what it looks like, but we need that information. I'm lying a little bit. There is one way to see through the ice that's pretty powerful, and it's basically based on radar. So you mount a big radar under the wings of an airplane, and it emits a signal that will penetrate the ice. And when it comes back, we can interpret this as some sort of X-ray. So here, in that image, you can see the air, you can see how deep the ice is, we have incredible details in the bedrock. So it's really a wonderful method. But we only get information directly underneath the aircraft. There is no information about the sides. What you're seeing here, all these colorful lines are all the lines for which we have measurements of the bed. So these represent 50 years of international campaigns, very costly international campaigns, to try to determine how deep the ice is. And you may wonder, why is he complaining? We have so much data, but this is Austria. We have to remember that these ice sheets are huge, and there are many places where we don't have any measurements for within a radius of tens, hundreds of kilometers. And that's making our life as modelers difficult. I'm going to talk to you a little bit about models, because as I told you earlier, I'm a modeler, and when I was a graduate student, I developed with 2 colleagues a new ice sheet model that was supposed to be better than anything that had been done before, more accurate, with better physics. And to put it in a nutshell, a numerical model is based on fundamental physical principles, like the conservation of mass, conservation of energy, and basically the conservation of mass. If there is one bad summer where there is a lot of melt, the conservation of mass tells us by how much we should lower the surface topography of the ice sheet. So in the model, we were ready to run it. It was a beautiful model. We were ready to run at a higher resolution than ever before. And we ran it forward, but Greenland was gaining mass, when clearly, when you look at every single observation, it's supposed to lose mass. So we were really like, what is going on? The model is wrong. Is it a bug in the code? Is it the physics? Are we missing an important physical process? What can it be? And it's very difficult to narrow down why the model is not behaving the way it should. So we spent months trying one by one every single hypothesis, and we had to come to the idea that it was the poor representation of the bed topography, especially where we did not have measurements. What we had was not good enough, was blocking the model from flushing that ice towards the ocean, and as a result, the ice was gaining mass. So we were like, okay, what do we do? We're not going to spend thousands of airplanes and measure the whole of the ice sheet within a resolution of a few hundred meters. It's not going to be possible, so what do we do? And by accident a little bit, we developed that method. Basically, in the mass conservation approach, what we do is we look at the ice speed. We can get that from satellite. It's very easy to know how fast the ice is flowing. We combine that with ice depth, and that gives us the thinning rates, so by how much the ice gets thicker or thinner. And we had that eureka moment. We thought, okay, we know that mass conservation is good. I mean, it's a physical principle that's always verified. We have ice speed. We have the thinning rates from satellite interferometry. We know where the ice is thickening or thinning. So why don't we move these terms around and say, let's use the same physics, but our unknown, instead of computing the thinning rates, we now compute the ice depth. And so we were able to use that method to fill in the gaps where we did not have data, where we did not have any measurement, but based on that physical principle and on combining other data sets that were not used in the past to try to map the bed. So after years of sweat and many sleepless nights, I managed to map the whole ice sheet of Greenland and Antarctica at an unprecedented level of resolution. So I'm going to show you here a few results. This animation shows you the west coast of Greenland. So to your right, I believe, is the ice velocity from satellite, and then to the left, we peel off the ice, and you can see the bed. So everything that is blue means that the bed is below sea level, but there is no ocean there. Remember that it's a fjord that's full of ice. And what you see is we have these fjords, these valleys that we did not know about before, for many of them, extend sometimes for tens or hundreds of kilometers. And so what this means is, as the ice retreats, because the bed, these valleys are so deep, they will still be in contact with that warm water that is at depth. Under Antarctica, the landscape is pretty different. We don't have that many narrow entrenched valleys. What we have in many places are these very wide valleys, big basins that are below sea level. You see how everything here is blue? So we have a pile of ice on top. It's grounded ice, but the bed is below sea level. And this is a glacier we're particularly worried about, Thwaites Glacier, because it's been thinning and retreating and accelerating over the past decades. And you see how upstream the bed gets deeper. Retrograde bed slopes, if it starts getting into that region, there is no stopping it. In East Antarctica, a lot of the bed is above sea level, but we found a few troughs, a few valleys that we didn't know about. This one is Ninnis Glacier, but there is another glacier, Denman Glacier, that scientists knew it was deep, but we never knew. We've never been able to figure out how deep it was. The radar that people were using could not detect how deep the bed was because it was just so deep. And so by combining these data sets together, the conservation of mass, we were able to map for the first time this deep canyon that you're seeing here. And it's more than 3.5 kilometers below sea level. So there are places that are deeper under the ocean, but this is considered a continent. This is land ice. So that's the deepest point on land that has ever been mapped. So overall, we uncovered the landscape hidden beneath the ice by combining data sets together, by looking at physics, by looking at remote sensing from satellite interferometry, by using modeling. We combined disciplines together. And when it comes to climate change, we're facing many challenges, and we have to be creative. We have to have more collaborations, more cooperation across disciplines in order to overcome the challenges we're facing. We discovered major features. We discovered canyons, mountain ranges, valleys that we did not know were there, and they have major implications on future sea level rise. But if the shape of the bed preconditions their stability, now we know which region may be more vulnerable to climate change, which one may be more protected. We have to remember that it is our actions today that will determine the fate of these ice sheets. They're not melting because of the bed. They're melting because of the concentration of carbon dioxide in the atmosphere. So yes, our future lies underneath the ice, but we should do everything in our power to keep the ice there. So let's try to keep this landscape hidden for as long as we can and reduce future sea level rise for the next generations. Thank you.